Hello and welcome back to Unit 13 on angular momentum. In this part of Unit 13, we're actually going to introduce the concept of angular momentum. Okay. Angular momentum occurs whenever there is not necessarily even a rotation, but a change in the motion that results in a change in angle of an object. We can think about the angular momentum of a particle or for a solid object. For a particle, the angular momentum, capital L, is found by the distance from the observation point, if you will, so R, cross the linear momentum. Remember, because it's a cross product, that will be in magnitude RP sine theta. If we're dealing with a solid object, then we get a formula for the angular momentum that is more akin to the linear momentum. Remember, linear momentum was mass times velocity. So angular momentum is the moment of inertia multiplied by the angular velocity. Okay. First off, let's consider a particle. A particle moving along a line that is a distance y from the observation point. Okay. As it moves, the angle theta changes. So we have a change in angle, therefore we can define an angular momentum for this object. In this case, remember, R points from the observation point to the object outward, so the radial vector is here, and the momentum is along the line of travel. That would be as shown here by the blue arrow. If we think about angular momentum being in magnitude RP sine theta, I'm going to rearrange this a little bit. P is R times sine theta. Okay. I have a beautiful triangle right here. Okay. Regrettably, my angle theta is defined outside of my triangle. So I'm going to define this angle phi, where phi is going to be 180 degrees minus theta. And now I'm going to remind you of a trig identity, that the sine of 180 degrees minus theta is equivalent to the sine of theta, or in other words, sine of phi equals sine theta, which is nice because phi is inside my triangle. If we now look at the sine of phi being the side opposite, that would be y, divided by the hypotenuse, r, you can see that the value of r sine theta will just be p times the value of y, the distance the line of travel is from the observation point. If we keep moving forward, the angle again changes. Again, here the angle is 90 degrees. The radial vector is upward. There's my 90-degree angle. Here r just equals y. So L again just equals p times y, or you can think about it as r p times the sine of 90. Sine of 90 is 1. Okay. Lastly, if we move past the observation point, again, theta is outside of my triangle. However, if we compare this angle to that angle, those have to be equal. So I again have L equals RP sine theta, but sine theta is going to equal the side opposite, which is y, over r. And therefore, the angular momentum is r times y. I've gone through this particular example in a fair bit of detail because it always puzzled me when I was in college and learning this for the first time, how something that could be traveling in a straight line could have an angular momentum. And the key is to look at the angle that the vector r makes with respect to the momentum and realize it does change relative to the observation point. Okay. Next, we're going to look at the relationship between angular momentum and torque. Recall when we looked at linear momentum, we had a formula that said a force, or the net force, was the derivative of the linear momentum. Therefore, it should not be a surprise to you that torque is going to be the derivative of the angular momentum. If instead we look at this as a change in, it makes this a little bit easier to see. Okay. If there is no torque, there's no net external torque, then that means that this has to equal 0. Okay. Okay. In which case, delta L equals 0. Or L final has to equal L initial. Final angular momentum has to equal initial angular momentum, which means we just derived ourselves a conservation law. The conservation of angular momentum occurs when there are no external torques acting on the system of interest. In the next two parts, we're going to do a bunch of examples illustrating the concepts covered in this part, including those using conservation of angular momentum.